something on statistics where it's better in the ultrasound second term there. I found an interesting fact actually. You know, Paul was born in Birmingham, UK, that is, which is 40 miles from where I'm born. So obviously, if you were born in around there, you either joined a heavy metal band or became a Bayesian statistician. I actually did both.
Well, I know you did both. Yes.
So Paul is fellow of the American Statistics Association. He's won many awards, including I won't pronounce it, the CRM bit, the SST I could probably manage, but the CRM bit is the French bit. That would be offensive if I did that in statistics. And in 2020, he was the gold medalist at the Statistical Society of Canada. Paul is one of a rare breed of people who not only just theory and methods, but also Bayesian statistics, but also contribute substantively, particularly in medicine and epidemiology, probably environmental health as well.
A little bit.
Yeah. His research interests include Bayesian methods, causal inference, saliva analysis, evidence synthesis, measurement error, and partial identification. I think this is really impressive. Paul, since 2014, has been the statistics editor of the journal Epidemiology, which is one of the best journals in the field. And I've published a few papers there, and that's a really important role because you have really impact there. You can change the way people do stuff. He's also written a couple of books. I won't give the full titles because they're kind of long, but measurement error, myth classification, epidemiology, and then more recently, Bayesian Inference for partially identified models. And that's some of the stuff, that's what Paul's going to be talking about today. So his talk's entitled Bayesian Inference when parameter identification is lacking and narrative applications, methods, and theory. Thank you.
Thanks so much, John. Very kind introduction. Can people hear me in the room and online? Okay, cool. All right. Yeah, so I will talk about partial identification today and trying to make the point that this does transcend applications and methods and theory. I think John has maybe already covered this slide for me, but the things I've been interested in over the last, I guess, many years now tend to fall into one of these five buckets. But the application motivations do tend to come from public health and epidemiology and those sorts of fields. And in a way, the more something's kind of in the heart of this jumble, the more excited I get about it. So really, this talk has 4 parts. And start with a simplish example of a partially identified model to try and get us all sort of on the same page. I have a few remarks about the really applied side of things, although this part 2 is a little bit short, but talk about being involved in some applications where these models arise, and also being in a collaboration where we're trying to talk about guidance for other people who might need this sort of thing. Part 3, I have an example that kind of spans, in a way, the whole arc from an applied problem to some theory. And then part 4 is just a little bit of a highlight of some more theory that's actually kind of old, but I'll tell you why I'm talking about old stuff. So that's the plan, parts 1, 2, 3, and 4. So part 1, we'll try and be quite concrete. To start with, maybe we're looking at a very simple data structure. We just would like to know what's going on with the 2x2 table, stratified by X and Y, but we're worried that we can't measure X necessarily as well as we would like. So we're worried that the thing we do observe, the X star, is sometimes different than the thing we wish we observe, the binary X. And so the actual data set, this is fictitious, but just to make things concrete, let's say you had this data in your computer on your or on your piece of paper or whatever it would be. You have the X star and Y table, but you really are interested in the relation between the X and the Y. And we'll make it even one step further simple, just to try and make a point. We're going to presume that the problem with the X star is not its sensitivity. It's perfectly sensitive. If the X is 1, then the X star is 1 for sure, and we know that. It's the other situation we're concerned about. We're concerned that the specificity may be below 1. So it may be that in some cases X is truly 0, but we measure a 1 erroneously. And you can imagine this kind of asymmetric setup could arise if you're asking people to their face something about, are you partaking in this virtuous thing? And you can imagine that if they are, they'll say so. If they're not, they may not give you the truthful answer. So anyway, short answer, short summary is we want to take this data and do something with it. And in particular, we'd like to infer the XY association, as I said, but we're a bit stuck in that we don't actually know how specific that measuring device is, how specific the X star is as a measure of X, and we don't even have a small validation sample. We never get to actually observe the X itself. But you can imagine if you knew how bad or good the measurement was, then you could proceed, right? If you knew lambda, then you can map back and forth both ways, prevalence of the thing you're interested in, given Y, back and forth you could map with the prevalence of the thing you measure, given Y. And so in particular, if you'd have a likelihood for your X star given Y data, and you're away to the races. And so in particular, doing a sensitivity analysis is sort of almost trivial here. I could postulate different values for this lambda and just see what happens. And in particular, I could report a posterior on my target parameter, which I'm going to take to be the log odds ratio between X and Y. I could report a posterior based on the data I see and based on the presumed value of this parameter. The only trouble here, I will get in a terrible tongue twister situation, because in this particular instance, you might refer to lambda as the sensitivity parameter, because it's the thing you're varying in your sensitivity analysis, but it's actually the specificity of the measuring device, and the measuring device has perfect sensitivity. So there's a little bit of a language challenge there. Anyway, here's what you get. Start at the top here. If I presume my data are perfect, if I presume the specificity is 100%, there's no problem. I get this point estimate of my target parameter, and this, I think it's 95% credible interval, no problem. As I successively presume smaller values for this specificity of the measuring device, my answer changes. And just as sort of a sanity check on this, for those of you who've talked about measurement error in various contexts, this is changing the way we would expect it to change. If we know that simple measurement error pushes estimates toward the null. So as you try and adjust more and more, your estimate will move away from the null. So that makes sense. And we also know that having noise reduces knowledge. And so it's no surprise that if you think your measurement is really noisy, you'll get a wider credible interval, say, by the time you get down here. So maybe I'll just pause there. Is there anything about the setup that I can help people with or try and clarify? We're okay? All right. So in a way, low-hanging fruit would be to turn this into a Bayesian problem. Instead of just fixing different values of lambda and seeing what happens, I could put a prior distribution over that lambda and do the Bayesian analysis with that lambda as one of the unknown parameters, and we'll get an answer out. And in particular, we would get a posterior distribution of the target parameter given the data. And I like to use this phrase, seamless uncertainty management. You can think about your posterior variance there, having these two pieces. And there's a piece that's kind of the usual piece that we get because we don't have an infinite sample. But there's also this second piece that's the uncertainty because lambda isn't known, right? As you change the lambda, this thing wiggles around. But both those things are accounted for if you report out this as your measure of posterior uncertainty, or if you build a credible interval that goes along with that. And we can do that. And for this particular data set, it's not actually super exciting. I'm doing this in the most simple and naive way. I'm just saying that I'm going to take these 5 possible values for the specificity that we had before, and I'm going to put a prior on those, which gives 20% weight to each of the possibilities. So a discrete uniform prior on these 5 values. And the red circles here are just to guide you about how much weight each value gets in the posterior. And this is not a great punchline because I've done this, and these circles are about the same size as each other. So I've started with a uniform prior on this lambda, and I've got more or less a uniform posterior as well. It's not exactly true, but it's very close to being uniform. And so it's no big surprise that when I report out my final answer here that's supposed to synthesize both sources of uncertainty, I get a point estimate that somehow compromises between these ones, and I get a width of credible interval that somehow compromises between the skinniest one and the widest one. Okay. Questions to that point? So not super exciting. On the other hand, we can rinse and repeat. We can do this with a different data set. And just for sake of illustration, here's a different data set. And I do exactly the same calculations. And it doesn't quite come out with the same qualitative features. And the thing that jumps out, well, two things jump out. Maybe the main thing is that I now have 4 big circles and 1 little one. So whereas in the prior, all these different values for the specificity get equal weight, this smallest one gets discounted in the posterior. And in a way, that's quite fortuitous, because that's discounting this inference, which is massively, massively wide. And so that's kind of a fortuitous thing. So when I combine across the 5 values, this is getting downweighted. And so my interval is somewhat narrow still. But the point that I want to get people thinking about here is that it feels like sensitivity analysis, right? It feels like the data can't tell you anything about how misclassified the X is. You don't have any validation data. Yet, if for this particular data set, we get a little bit of updating prior to posterior about this thing. In the first data set, we didn't. So data set dependent behavior. And in fact, that's what I've got here at the bottom of the slide. I would tend to refer to this as we're stuck in the middle with Bayes. This is somewhere in between sensitivity analysis and inference. It's got a little hint of inference in the sense that this is downweighted compared to the other ones, but it's still got a lot of the feel sensitivity analysis. Okay. What's under the hood here? Well, this is a simple enough problem that you can kind of see fairly readily why this behavior is arising. And the trick here is just to reparameterize, and you can see what's going on. We start out with the more obvious parameters, where we're talking about the things we're interested in scientifically. We're talking about the prevalence of X in the two, if you like, in the controls and the cases. But if we reparameterize to talk about the prevalence of the thing we actually measure, then we can kind of see what's going on. We start with a prior in the if you like, the scientific parameterization that transforms over to this new parameterization. The data speak to this thing, not this thing, and you've kind of decomposed what's happening. And even though we have this conditional independence, even though the lambda doesn't influence the data in this parameterization, you still have this kind of indirect effect that if you've got a priori dependence between the two parameters, that's going to carry over. And you can still have some updating. You learn directly about the phi, and through this a priori dependence, you learn something about the lambda. And it's not like this is a sort of artificial made-up dependence. If I start out with basically anything reasonable in the original parameterization, I will force this a priori dependence because, in fact, the support of this thing depends on the thing you do learn from the data. So it's not like sort of an arbitrary modeling choice to put that dependency in. It just pops out as a part of the structure of the parameter space, basically. And in fact, we can even sort of go behind the curtain a bit more here. So we can't consistently estimate this specificity, right? It's more or less a sensitivity parameter. but it is bounded below by something we can't estimate. And so if you work out the math, lambda is bounded by bounded below by the bigger of these two things. And these things you can learn from the data, right? These are the observed prevalences of X star in the two groups. And you can also kind of get a feeling then about why it could be that in one data set, you didn't get any updating, and in the other, you got some. Depending on parameter values, this may or may not take a bite out of the a priori support of this parameter. But you can even forget about the Bayesian stuff here. There's no real magic here. If you did have a measuring device that had perfect sensitivity but lousy specificity, you would be generating some X stars equal to 1, right? Regardless of actual prevalence of X, and you would be generating a substantial number of apparent positives. So these things, which way around? I'm getting myself in knots, tying myself in knots here. If you right, you can't measure. Why am I struggling with this so much? Yes, if you have if you really had low specificity, hold on. Does this make sense? I thought I had it straight in the words here. Okay, let me just make sure I've got this right. If your measuring device was lousy, you get these apparent positives, no matter what. And what does that mean? That means these terms are big, so this thing is small. Oh, help me out, Pam.
That, sensitivity, then the probability, right? Is X star exposure or like the false?
Well, X star is it's what you measure, right? Well, there's some unknown prevalence of the X itself, right? But I guess the point is no matter what that unknown prevalence is, if the specificity is lousy, you will get some X star equal, which way around is it? If the specificity is lousy, then you are generating a lot of apparent positives, which are X star equal to 1. Regardless of, yeah. And if you're generating a bunch of those things, why am I so stuck on this? It made perfect sense when I wrote it down. Give me one more sec. I want to argue by contradiction here, right? I want to say that you know what? I'm not going to do this in real time. Let me say it this way. This is a mathematical inequality that is, right? And so the point is that depending on what these things are, you may or may not get information about the lambda, right? If these things are really big, you're not really learning anything, but if these things are small, it rules out the lambda being close to 1. And the homework exercise is to match up this sentence, which I can no longer parse, with what's in there. And I'm going to move on because I'm making this worse for myself, not better. Whew. Okay. Moving right along, this is actually a simple, well, I was going to say simple example, but I didn't make it seem simple, did I? Moving along, this is quite common. Many of you will have encountered this in one form or another, that there are these bounds. There are parameters that you can't estimate consistently, but you can consistently estimate lower or upper or both bounds on these things. And in fact, there's a rich history of this in econometrics. There's a whole book, particularly by Mansky, that talks about this sort of stuff. Now, one thing that is sort of relevant for today is that for a Bayesian analysis, even though we could do it, I don't want to see this slide ever again, but even though we can do it in this simple problem, there'll be other problems where we're just specifying models and priors and putting it into MCMC and turning the crank, and that's all fine. We don't have to have a mathematical form for those bounds. It'll come out in the computation that as the sample size grows up, your posterior must live between those bounds. So you don't necessarily need an explicit form for them. On the other hand, there's sort of a folk theorem that says when you try and do these using very standard software packages, it tends to be a mess. And in particular, if you just start with the so-called scientific parameterization and don't work out this structure in the parameter space, you may end up with your MCMC mixing quite terribly, and that becomes a frustration. So it's, in a way, it's clean in theory, but in practice, it can be much dirtier. Okay, let's move on. Part 2 is just a little bit of flavor about the about how these things go down in practice. And it occurred to me that over many years now, I've been lucky enough to work on various applied projects where it has this kind of flavor, that there's an X you wish you had and an X star that you actually get. And here are some of the examples. And I guess the point I want to make is that when you start talking to the experts in the area, you end up, in some way or other, you end up talking about identification. And you either reach the conclusion that, yeah, I know enough, or the assumptions I would need to get identification are reasonable enough that they're supported in the scientific area, and then that you can go with it. Or you say, yeah, wait a minute, at the end of the day, I don't have enough to go on here. I don't know how good or bad X star is as a surrogate for X. I'm going to have to go this, put a prior on it and see what happens route. So it can go down one of two ways, but the point is it's not for me to decide, right? It's not for the statistician to decide. It's got to be in consultation with the people who know whatever the topic is. And then the other thing I would say about the applied side is I've really enjoyed working in this, and I'm not just saying this because my Stratos boss is in the audience. I've really enjoyed working in this collaboration, the Strengthening Analytical Thinking for Observational Studies collaboration, which has now grown to be more than 100, mostly statisticians, biostatisticians, and has a bunch of topic groups. And in particular, there's a topic group number 4 on measurement error and misclassification. And the main, I mean, there's some other things that this group tries to do, but the main idea is to try and help researchers, applied researchers, kind of keep up with what's in the methods literature by knowledge translation and writing guidance documents in particular. And just as one example of that, here's a somewhat recent guidance paper from topic group number 4, which is, well, again, focusing in on this problem of measurement error, issues in implementing regression calibration analyses. And just to give you a little bit of the flavor of why this identification issue comes up there, as you get towards real problems, things get more complicated. And it's not just you have an X and an X star, you have an X and an X star and an X double star. And you have to think about, okay, this, that's me, isn't it? You have to think about, I've got one surrogate I can measure that's maybe quite noisy. I've got another surrogate for X that's maybe quite good. But how am I going to put all this data together? Particularly what conditional independence assumptions would cause me to end up with an identified model? Are those reasonable? If not, we have to back off and think about something that's maybe only partially identified. But again, we can't progress without knowing a lot about the scientific context. So that's just to give you a hint of how these ideas might play out in practice. All right. Moving right along, part 3. This is an example of recent work led by a PhD student who finished up, I guess, last year, about almost a year ago now. I've picked on this example because it does give this narrative arc. I'll show you something with a very applied flavor, and I'll show you something with a very theoretical flavor. And by the way, Daniel was great. So he led and I followed. That's the way it should be for PhD supervision, right? You want the student driving the bus. So start from the application end of the arc. And actually, Daniel had been involved in this applied project without any sort of involvement from me. And this is again, as to try and make a point, this is a little bit oversimplified. This is a randomized trial, and randomizing people who are experiencing homelessness, either to receive a one-time cash transfer or not. And the question is that a meaningful intervention in terms of their housing status at follow-up? I can't recall off the top of my head. Follow-up might have been 3 months or 4 months down the road. And we don't even have to put in causal inference language here necessarily. It's an RCT. If I could observe all the variables, I could just say, well, I just want to compare these two rates, right? I just want a risk difference. The complication is that the Y is prone to missingness. And in particular, for those of you with missing data experience, you know there's sort of this gulf between MAR, which is quite easy to handle, and not MAR or non-ignorable, which is sort of generally horrendous to handle. And there's particularly worry here that we may have possibly non-ignorable missingness, because you can easily imagine that the people who don't find stable housing are going to be harder to find at follow-up than the people who do. So there's kind of an intrinsic reason to think that that's a problem. And so we are worried that this missing at random assumption, conditional independence of the missingness indicator and the Y, that this will fail, conditioned on the things you do observe. On the other hand, there's a hope that there might be an instrumental variable here. We're using, and this is a little bit, again, for the sake of illustration, I'm not really sure that an age or a binary version of age is really going to satisfy the instrumental variable assumptions. But let's say for a minute that it did, we would be saying that maybe there's another variable that we can measure for everyone that is predictive of their missingness status, but not predictive of their outcome. And if we had such a variable, then that's going to help us out. And so I'm just going to show you, to get some flavor here, I'm just going to show you inference under 4 different sets of assumptions. Well, first is an absence of assumptions. So and in a way, this is not a difficult data structure, right? Again, I'm trying to make a point by keeping the data structure simple. We have binary data on 4 things: Y, R, X, Z. And so we could just, even thinking as Bayesians, we could just have all the cell probabilities we need, let's say for Y and R jointly given X and Z, and put, let's say, Dirichlet priors on those cell probabilities and do updating. It's conjugate, very simple. And if we did observe everything, fine. Of course, we don't get to observe everything. If you like, we get to observe the R given X and Z marginal, and then we get to observe Y only given R equals 1, right? We don't get to observe Y given R equals 0. And so you can quickly count up parameters here, and just unknown parameters here, data degrees of freedom here, and you don't have identification. But you could still turn the crank, right? You could still put do the Bayesian updating of the cell probabilities and get a posterior inference. Alternatively, we think MAR is probably too strong an assumption, missing at random. but that would fix the identification problem. If you did impose it, if you imposed this conditional independence, then again, you could do the counting up the number of parameters as a first pass at verifying identification. That's not actually a proof that something's identified, but it's a good first step. So I'll show you that one. I don't know if I didn't really know about Heckman selection models until I was involved in this work. But for those of you who've seen this, you can make some kind of linear model assumptions, and in particular, bivariate normal assumptions for the underlying continuous variables that you think about the binary things as being truncated versions of those continuous. So you think there's an R tilde and a Y tilde that are continuous. The R and the Y come from thresholding that. If you think about a linear model with a bivariate normal dependence, then you get this thing, plus this assumption that Z's an instrumental variable. And then finally, this is sort of the new one in the mix here. Well, one of the new ones. So there's actually more than these choices in the paper. You could do a Bayesian prior that says, well, I'm not so sure this is a great assumption exactly, but it maybe isn't going to be violated too much. So you can put a prior in that says that this association will be small. And this is a useful one for this application. You could put in to your prior constraints, if you like, that you know the direction of this association, because we think we do in this case. We think it's the unhoused people who are more likely to be missing at follow-up. And so you can do a Bayesian inference under all these settings. The answer is not sort of super exciting, except to say that well, these labels are very technical. This is the A. This is the no assumptions. And you get, as you might expect, you get a wider. This is 95. The blue one is 80% credible intervals. Not surprisingly, you get narrower things under these various different sets of assumptions, assuming MAR, the Heckman model, and this other new thing. So the point is that there are various ways that you can kind of sharpen your answer if you're willing to trade off with various assumptions, right? Put various assumptions in, put priors in that talk about the extent to which assumptions might be violated. But interestingly, maybe even though we know this one's not identified, we know this one's not identified, we know these ones are, but in practice with a finite sample size, it doesn't sort of jump out that, oh, this one is such a good assumption, it makes things identified. It doesn't really give you a narrower answer than these other ones. So everything's really kind of problem specific with these things. But then also in this paper, there's a bit of a theory end to it as well. So there's some of this working out of the bounds, like we saw in the simple problem. So working out exactly, where if the prior lives between here and here, work out that the posterior, if you had infinite data, lives between here and here. So there's some of that. This is something that has always been of a little bit of interest to me, and we tend to think of these. We tend to put assumptions as something that, well, we tend to label assumptions as either being testable or untestable, right? And we tend to say things quite generally like, oh, well, the no unobserved confounders assumption is untestable, or the missing at random assumption is untestable. And that is mostly true, but there's a bit of nuance in the sense that in these kinds of problems like we saw on the previous slide, you can compute, because you're doing this Bayesian inference, you can compute Bayes factors that talk about the thing with the assumptions versus the saturated thing. And so in particular, we tend to say that whenever instrumental variables arise in different contexts, but we tend to think about, oh, saying something is an instrument is an untestable assumption. Well, mostly yes, but you can show that from a Bayes factor perspective, when you're comparing the hypotheses that Z is or isn't an instrument, you can get a Bayes factor whose limit, large sample data limit, is something other than the obvious suspects. So here, meaning that 0 and infinity would mean that it's a testable assumption. 1 would mean it's a completely untestable assumption, but we can get limits that are in between 0 and 1 or in between 1 and infinity. And so there's a degree of testability. It's small, but it's not completely absent. And in fact, this is a shameless shout out. I have a paper that really kind of digs into that a bit more. And then just the final thing on this one that I find quite interesting is when I was in grad school, and I remember learning about the Borel paradox and thinking, oh, that's kind of neat mathematically, but I can't ever see that being of any value in any sort of practical sense. Turns out, in this problem, it kind of comes into play. So in particular, you start with this saturated model where all the cell probabilities are allowed to be whatever. And then you want to talk about, well, I'm going to compare that with a model that says Z is an instrument. And in terms of the cell probabilities, Z is an instrument could be expressed as some sort of risk difference is 0, or it could be expressed as some sort of risk ratio is 1. And in real world intuitive senses, that's the same thing. In conditional probability land, that's not quite the same thing. That's exactly what the Borel paradox says. And so you can get slightly different answers depending on whether you take this view or this view of what the prior should be under a particular assumption. So that's kind of a point of interest. Okay, so I think we're doing okay-ish for time. I think we are now to part 4. And we've talked already about bounds, right? And the essence of the bounding kind of arguments is that, to review, we start out with some set of parameters that we think make scientific sense, right? That kind of come out obviously as part of the problem. If we have enough structure that we can identify a new parameterization, so a proper parameterization, we can go back and forth, such that the data only depend on the first thing, the phi, and not on the second thing, the lambda, then what we'd like is to be able to bound the thing we're interested in, working in this new parameterization. We want to, well, the target parameter will generally depend on both those things. But if we can squish it in between a lower bound and an upper bound that depends only on phi, then we are gaining something, right? We know that we can learn these things from the data. So even though an infinite amount of data will not get us to the right answer, an infinite amount of data will get us to an interval that contains the right answer. And that interval is narrower than the prior you started out with. So that's kind of the essence of this bounding problem. But then the thing I've been interested in off and on is in the econometrics and much of the stat literature, this is the end of the story. People say, well, okay, I've figured this out, what the form of this B sub L and the B sub U, and I'm just going to get my phi hat and stick it in and give that as an answer. And then there's some issues about exactly what does that mean, because you worry about the phi hat not being exactly the same as the phi, but that's the essence of it. Whereas in the things I've been showing you, you are actually generating a posterior distribution. And we know in the limit of large data, that posterior will live between these bounds. So the question is, how much value is there in the shape of that posterior compared to just reporting the bounds? And so here's my excuse for telling you something ancient. This part's not so ancient. So a couple of years ago, I wrote a commentary on someone else's paper, and this issue was kind of central. Do we just want to try and bound the target parameter between two things? Or do we really want to try and generate inference that might favor some values in that interval over others? And so this was all kind of words. But then I remembered that a long time ago now, maybe can't read that in the room, but this is 2014, I tried to take a more mathematical dive into this. And so I thought it was worth just kind of revisiting that for a moment, and I'll tell you why. This is a different problem involving RCT data. The details are not super important. They're just kind of it's a model and prior that we're going to to use to make a point. But for those of you who have seen this sort of thing, this is your kind of typical issue of compliance in a trial. You assign people either to 0 or 1, control or active treatment. Sorry, the Z is the assignment. You randomize people to either control or active treatment, but they may or may not comply. And in particular, there's this principal stratification idea that we're going to think about a population where really there are 3 subpopulations. There are the people who will comply with their treatment assignment. There are people who will never take the active treatment, and there are people who will always take the active treatment. And you can probably relatively easily convince yourself that this is going to be one of these partially identified situations, because you are not going to know for sure. For some people, you're not going to know which of those strata they actually come from. Question? Well, complying means that you're assigned in either a 0 or a 1, right? A complier will always do that. So a complier is defined by x equal to z, whereas an always taker is x equal 1 no matter what, and a never taker is x equals 0 no matter what. Does that make some sense? Okay. And well, you will notice, for very good reason, I have not included defiers on this list. So you could, in principle, think about people who will always do the opposite of what they're told, like toddlers sort of thing. And it turns out the math on this gets way, way more complicated if you think that there are defiers out there in your population. So we're not going there. But for instance, let's see if I can get this one right. If you see, let's see, right, if you see a person's in the 1-1 situation here, you don't actually know what subpopulation they came from, right? They may be an always taker, or they may be a complier. Whereas if you observe that someone's in this row, you know they're a never taker, right? Because they were told to take treatment and they didn't. Anyway, the point is you don't have enough structure to know which of the subpopulations each person is in, and therefore you don't have a fully identified setup. But what you do have is a picture like this. So for that data set on the previous slide, we start out again with sort of priors on cell probabilities, and in particular, that induces this red prior density on our target parameter, which again, just to remind you quickly, is the average causal effect. So you're trying to compare what would happen if everyone took treatment versus no one took treatment. So you start with the red as the prior, you apply that data on the previous slide, and you get the blue posterior. So you get quite a bit of updating about the target parameter. And then you do this more mathematical thing, and you think, well, wait a minute, what if this is, do I have the sample size on the previous slide? Yeah, I do sort of. If I add up these 4 numbers, that's the sample size. So it's, a few hundred. So my blue answer is based on a few hundred patients in my study. I can mathematically say, well, what would happen if I crank that up to an infinite number of patients in the study? But I'll just keep the cell probabilities the same as in the actual data, just as sort of a thought experiment. And it turns out I will, in the infinite data limit, I get this green posterior density. And in particular, I've highlighted that it lives between here and here, because that is this interval, this based on these 2 bounds, or the lower bound and the upper bound. If I'm non-Bayesian, I simply learn that the target's in here. If I'm Bayesian, I think it's a bit more likely that it's in the middle and to the edges, and it just happens to have this weird trapezoidal shape. And then it's also maybe worth noting that you also have to think totally differently about study design in these kinds of problems, because you would be wasting resources to collect much more data here, right? The data you've got already give you the blue thing. The theoretical limit of what you can get is the green thing. And so you could spend an awful lot of money on further data collection and get basically nowhere. because of this lack of identification. Anyway, the thing I really want to get to, we've got, I guess we've got a little bit of time, yes, is that in this problem and others, you get this kind of funny behavior. You could have, depends on if you want to think about it in terms of data sets, you could have two different data sets. If you want to think about it in terms of true values, you could have two sets of true values in the parameter space, and they could generate the same interval as the identification interval, but different posterior distributions across that interval. And so in particular, there's a point in the parameter space where you get the taller trapezoid as the limiting posterior density. And there's another point in the parameter space where you get this shorter trapezoid as the limiting posterior density. And that to me is a bit of an aha thing, because you say, well, wait a minute, if I don't take the Bayesian point of view, all I'll report out is that the parameter lives between here and here. So it hints that there is a bit more information in the data than just the bounds. And I think I'm going to, yes, I'm not going to, well, if you want to know what the blue thing, I think read the paper. It's a little bit convoluted. But the point being that the fact that I can get different answers, the two different red answers, hints that there's information that is accessible to me as a Bayesian that's not accessible to a non-Bayesian. And so we try and sort of quantify that in a more rigorous way. And we talk about some measure of Bayes risk. And in particular, we talk about what's the typical height of the posterior density at the true value. And we average that jointly with respect to parameters and data, as we tend to do in Bayesian decision theory, and talk about Bayes risk. And we pass to the large sample limit. And we can actually make a quantification of how much that shape of the posterior helps us out. And again, I'm going to skip a little bit of this, but we can really kind of get at what do we gain by reporting the posterior versus reporting a different distribution that's just kind of an intuitive thing based on the bounds. And the two intuitive things based on the bounds would either be a uniform distribution between the bounds. So forget about those trapezoids, just make it completely flat. Or you could think about truncating the prior density from its whole space to just between the bounds. And that would be sort of pseudo-updating, but it turns out to be not exactly Bayesian updating. And when you do that, you can make these quantifications. And so just to cut to the chase here, and I'm going to end up, I'm skipping out this business about being coarse versus full. I'm going to compare being a non-Bayesian to a Bayesian. And if I start with, if I'm comparing the Bayesian answer to instead just reporting a uniform distribution between the bounds, I end up getting this much plus this much gain in terms of this Bayes risk. And so it's 10%, it's not nothing. Although this part is the underwhelming part. There's this kind of intermediate step that I'm only getting a little bit of extra information. Or you can change, instead of looking at a uniform distribution, you can look between the bounds, you can look at a truncated prior density between the bounds. All that is to say, I still think there's an unappreciated thing here. And so I'm just being sort of grumpy and complaining that I wrote this paper 15 years ago and no one paid attention. But I think it needs a reboot. And I think it needs a reboot just to go back, because I think there is interest in the question sort of in sort of qualitative applied terms. Should we be just working on these bounds, or should we try and have a distribution across the bounds? And there is scope to have some math to back that up. My math didn't catch on the first time. This is one of my least cited papers, so I think it does need a reboot. Okay, so what have we done today? Again, we went through 4 things. We had a simple example of how these partially identified problems might look. Although you'll notice that even though it was quite simple in structure with these 2x2 tables, I still screwed it up, right, when I was trying to get to the explanation. So these things are not intuitive often. I talked a bit about the applications end of things and having to get in there and talk to the subject area person about, what are the reasonable assumptions and does that get you full identification or just partial? We went through some of the highlights of this non-ignorable missingness in the outcome model where there's both an applied end and a theory end. And then finally, we tried to talk about the advantages of actually doing Bayesian inference rather than just trying to figure out the parameters between here and here. Okay, I think I should probably quit while I'm ahead and stop there, but I'm very happy to take questions.
Yeah, thanks. Interesting talk. I have a quick question about your very interesting example. So,
Mhm.
In that case, I'm just curious, is there a way to like parameterize your sensitivity and parameter like differently so that's like the range doesn't like decide on the range of your also?
Yeah, that's a really good question. And I'd say the answer is yes or no, yes and no. So let's go back to there. It's quite early on, right? Yeah. Right. So it's kind of here you're asking me about, right? Yeah. And you could, okay, you can't do it with this parameterization because, well, as I say, the support of the one thing depends on the other, so you can't do that. You could try and model, well, not even model. You could try and do a prior specification that breaks that dependence, but I think it would be very convoluted because you would lose all sort of scientific meaning of those things. I have thought a bit about this because you can sort of say, well, I don't think I can really do this in a hand-wavy way, but there are a couple of papers in the literature where people argue that you should do this. You should try and break up, change the parameterization, and then explicitly try and make the two things independent a priori. And my pushback on that is that even if you can do that, I am pretty certain that if you take that new prior that that prior you've constructed that way, and you transform it back to the things you can make sense of, that you're going to get some bizarre thing that doesn't make a lot of sense in this space. Well, my point, yes. Well, so it's mostly an issue of support. But if you really worked at it, you could kind of break that. You could take this thing. Let's see. Well, you could instead of having the lambda, you could have a lambda that kind of scaled relative to these things. Blah blah blah. If you really worked at it, you could break that dependence. But I think you just end up with something bizarre when you transform back to the original space. Great question.
So I guess I have two different questions. It was a very interesting talk. I mean, parallel context and probability problems, perhaps in other contexts. So one question is maybe those results at the very end where you had a gain of 9%.
Mm-hmm.
When I understand that this support, the asymptotic support of the posterior is in some sense more specific, in the sense of likelihood specific, and does not depend on what specific choice you make for the non-identifiable parameter.
Mm-hmm. Yep.
Right.
Yep.
But while the support is it truly with shape is also independent of what prior you choose? So say that I choose a prior that has support that completely far away from that, region that you were showing us. Won't that be a prior?
Well, so,
could make that of one? Because all the possibilities you showed us, I guess I thought that.
Yeah.
In the middle of this, right?
Yeah.
So I came back.
Yeah.
Badly.
Yeah.
Oh, you're gonna get something bad.
Yes, I think I completely agree with you. You would not get those symmetric trapezoids anymore. The trapezoids are a very kind of special case that come from using basically a uniform prior on those cell probabilities. However, even if you change this to some other prior, you're still going to have the issue that you can have two different points in the parameter space that lead you to the same interval, but a different shaped posterior. Yeah. But you're absolutely right. The trapezoids are a nice, simple mathematical case that comes out of having uniform priors on those cell probabilities. Yeah.
And I guess the second level of the question had to do with some of the discussion on testing the different models that, this was earlier in the talk when you.
Yeah.
So in my experience, so I've done a lot of work with factor models where you also have, naturally not identified
Mhm.
particular, you wanna synthesize, the factors you have in the model and things like that. And so in some sense, the take home message from practice is what you have to be careful is that the implied prior on the specified parameters in some sense is coherent across dimensions. If what you actually,
Yes.
when you know, identify will say
Yes.
many things are gonna happen.
I think that's exactly right. Yes. Yeah.
You have to care about what the implication is. for
Yes.
specified
Yes.
parameters.
Yeah.
So I wonder how that plays out here in that example that you were playing around, because I mean, is it true that the different priors, when you map them to the identified space, actually look the same or close enough? That because otherwise the base factor is kind of.
Yes. I think you're exactly right. And I don't think it's, so this comes up a lot actually. And I briefly mentioned, oh, I'm going the wrong way. Yeah, I briefly mentioned this paper, and that challenge is very explicit in this paper. That yes, you can have different models. In fact, in this paper, sometimes we're comparing 3 or more models, and maybe one is identified and 2 are not. But this issue completely comes up quickly. That it's yes, if the marginal prior on the identified bit on the phi differs between 2 non-identified models, then it's not so clear a base factor is meaningful. So I think it's absolutely an issue.
Question on Bayesian, but I'm gonna go to the other side, and you mentioned something that you may have that I don't, so that there's some more information in the shape,
Mhm.
versus
Yeah.
this bounding, and so I wondered if I could put out full decomposite intervals, there's this desire to just assume, oh, well, the true parameter is right in the middle, and this is just.
Yeah. Yeah. Yeah.
Value on the middle of the composite.
Yeah.
But I'm like, that's not what a composite is giving you. There's just people in this sort of region, and the reason it's important is because in science, they do small studies to justify the next study, and they will power the next clinical trial or whatever by looking at.
Yeah.
So I was wondering if people are doing pilot studies, if there's this missed opportunity by doing the composite intervals or something. To learn more about the shape, like the likely values, which we want. It's a really should be history of mode, and a Bayesian analysis as the parameter to power your next.
Yeah. So I think that's a really interesting comment, and I'm not sure I have a great answer, but I have another comment. One current project with someone at UBC is it's a little bit in this direction because my collaborator there is quite concerned about the plug-in nature of power calculations. And yes, and he's saying, well, shouldn't that whole posterior distribution from the pilot study be the input to the power calculation? And so I think that I'm hearing that's part of your issue. Yeah. Right. Yes. Absolutely. So I think if you take it seriously, then yes, I think you should be using that whole shape, and maybe maybe a Monte Carlo sample from that posterior is somehow the input into the power calculation to decide what happens next. Yeah. Yeah. Right. Yes. And incidentally, I will make one more comment about these. It's kind of weird that all those things I showed you were trapezoids, right? That's a little bit strange. It's actually, you can kind of demystify that a little bit. You've got these, you're basically, those things are kind of picking up the uncertainties in these things we can't estimate, and those things have uniform priors, and you start adding uniform things together and taking averages, and you get out. It's not completely nuts that you get out that particular shape. Yeah. Yeah.
Obvious on day one that you need to collect more data, individual level data. And so if you thought about the design aspect, just how much information you would need when you actually measure things, so even in the first example, how many people, if you got the exact X and the, how much, is there a minimum? I know it's probably going to be, well, it will be problem specific, but how much information you need so you can just tie down where, you know, destroy the uninformative.
So I think, if I'm not wrong, and I've got someone who can help me out here, in one of these Stratos guidance papers on measurement error, I think we have some verbiage in there about it's kind of a sample size inflation, that if you would need, if you need 1,000 people to power your study the way you want, if you measure the X, then there's an equation that links that to what you're going to need when you admit that the thing you're trying to measure is measured with error. Am I remembering that correctly, Pam? There's correlation, squared correlations and things in the, yeah.
You have the same power,
Yeah.
you would have had you measure the
Yeah.
precise X.
And there are some surprisingly general formulas there. I was a bit surprised at the time when we put this in the paper that you can kind of express things in terms of the correlation between the X and the X star, and that's kind of all you need to figure out the additional multiple you need of sample size to get what you would, to get the power you would have if you could measure the X itself. Yeah, it's not good. Yes, yes.
Gustafson's dead or alive, for instance, right? That's a huge loss of information, and so certain kinds of errors really are.
Yeah. 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 But it also, I mean, one of the points that I try and make, and I kind of fell into my own trap here, and without actually running these things down line by line, it's really hard to intuit the impact of 10% measurement or 20% measurement or whatever it is, and whatever your inferential purpose is. You've really got to go through it line by line to be sure we can easily trick ourselves and write things on slides that we can't explain later. It's a problem.
Which reminds me a bit, I mean, when you're thinking about one thing, you always think it's connected to everything else. So that makes me go, I'm teaching this theory class, and advice that I've been going through all those different types of like additional marginal factorizations. And there's kind of some link to that, I think, here, because I was thinking about the uniqueness here, what is it? I mean, I actually like conditional marginal stuff because it's very closely related. It builds on the particular problem, which is nice. The Bayesian say, oh, there's all these different likelihoods. How do you know which one to pick? But I actually like it because it kind of, it tunes itself to the problem at hand. But the problem is there's no formulaic way of doing it. Oh, here's where we would use a condition. You don't have to work it all out.
Yeah.
You have this moment of inspiration or somebody did back in the day. It's sort of similar to that in a way, right? Because it's not obvious how you do that parameterization.
No.
You could always do it, and you must have had situations where you're competing ones and you get to choose.
Yep, that's absolutely an issue. I have a current PhD student who is gamely struggling through a bit of that issue, and there are a lot of sentences in her thesis now that say things like, well, if a transparent parameterization exists, then we will do da 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 da. And that whole phi lambda thing, you can generally only do it in pretty simple toy problems, and it doesn't really get at the real issue that you build this, you build this realistic thing with random effects or whatever it is, and you put it into MCMC, and it doesn't run well, and you think, I bet this isn't fully identified, but how are you going to prove that? That's open question. Yeah. And also, yes, in a way, when you do that phi lambda thing, the phi is sort of unique, right? Because any phi that will work is just going to be a simple mapping of any other phi that will work. The lambda is a bit arbitrary, but at the end of the day, when you transform, it doesn't really matter in a sense, because you're going to if you transform back to the original parameterization, it's going to, as long as you're specifying the prior in the original parameterization, the phi and the lambda are just the coordinate system to do the calculation, right? And then you're going to transform back. So the choice is not super important if it works, if it has the right, properties.
Zoom to see if there's any.
Oh, sure. Yeah. Oh,